The Pennine Alps form the inner zone of the Alpine chain. Although many of these mountains, like the Matterhorn, are among the highest in the Alps, structurally they take us deep down into the very core of this mountain belt. On the southern side of the Alps, there are many valleys and gorges which drain off into the Po Valley in northern Italy. This is the Pennine zone. Some of the deepest Pennine structures are exposed in these riverbeds. The evidence of intense folding and deformation is everywhere in metamorphosed sediments and continental basement rocks, which were caught up in the collision between the African-Italian continent and the European continent. These two continents were once separated by an ocean which has been totally destroyed. But in the Swiss Alps, above the Zermatt Valley, there are a few scattered remnants of the ocean floor.
Most of the rocks in the Alps are what we might describe as continental, sedimentary cover and basement granites and gneisses. But here, high in the center of the Alps, there's something very different. For this rock is basalt, and these curious lozenge-shaped structures are pillows of the type formed when hot molten lava is erupted underwater. Their present shape simply reflects the amount of stretching, of deformation they suffered during this mountain building event. Compositionally, these are very similar to basalts erupted along mid-ocean ridges at the present time. This must be a piece of some ancient ocean crust. How then do alpine ocean floor basalts come to be here, some 2 kilometers above sea level, and apparently surrounded by continental rocks? In many ways, that's the key to the understanding the regional evolution of the Alps. For these basalts occur here, sandwiched between two masses of continental basement.
Before the continental collision that formed the Alpine Himalayan belt occurred, Europe and Italy were separated by an ocean. There was a subduction zone beneath Italy, and as the two continents moved towards each other, most of the intervening ocean crust was dragged down into the upper mantle. Eventually, the two continents collided, and a zone of thickened crust was formed to produce the Alpine mountain belt. In detail, the structure of the Alps is very complicated. In the case of the Pennines, the deformation was so intense that basement rocks were deformed along with the sedimentary cover and the remnants of the ancient ocean floor. Further to the north are the Helvetic Alps and the Pre-Alps. These include very large-scale structures which we examined in the last program. For the rest of this program, we'll just be looking at the rocks and the structures in the Pennine zone. The Zermatt Valley has been a popular tourist resort for over 100 years, dominated as it is by the most dramatic profile of the Matterhorn. And one of the great pleasures is the train ride from Zermatt to Gornergrat, a ride that takes you above 3,000 meters. The top part of the Matterhorn is part of the Italian plate, which now resides above the rocks of the European continent. Around the base of the summit pyramid is the layer of ocean floor basalts. The tops of all the high glaciated peaks along the north side of the Zermatt Valley are structures called klippen. These klippen are the remnants of structural units of the overriding Italian plate, which have been isolated by subsequent erosion. Under these klippen, below the permanent snow line, is the fossilized ocean floor, which in turn is on top of the European continent.
In the Pennines, we can view a part of the European plate that has been subducted beneath the Italian plate. The rocks here are about 80% basement. These basement rocks are very similar indeed to the ones we saw in the Mont Blanc and the Aiguille Rouge massifs. They consist of banded gneisses and banded schists of different types, intruded by massive plutonic rocks, mostly granites. The main difference here in the Pennines, however, is that these rocks have been very intensely deformed in a very ductile fashion during the alpine orogeny, and they have been subjected to metamorphism. The structure of the Pennines are as follows. The basement forms the core of large recumbent folds which close towards the north. These basement masses probably connect underground to the Aiguille Gauge and the Mont Blanc Massif. Here we have the Aiguille Gauge Massif and the Mont Blanc Massif in the north, and probably the Pennines connect beneath surface in that way. The Aiguille Gauge and Mont Blanc Massifs have Mesozoic sediments attached to them, and we have seen that the Mont Blanc Massif has been deformed and the Mesozoic sediments have been thrown into the large recumbent fold of the Morcle. These Mesozoic rocks of the Helvetics connect back into the Mesozoic rocks. These are mica schists, calcareous mica schists, which occupy very narrow, very tight synclines between the Penninic nappes. One very important feature of these synclines is that because they contain only Mesozoic rocks, they contain only alpine imprints. That is, the deformations in these Mesozoic rocks must all be alpine, and the metamorphic state of the rocks must indicate the alpine temperatures and pressures that were acquired during the alpine orogeny.
Because the high mountains of the Pennine zone are so heavily glaciated, it's often very difficult to examine the outcrops in detail. But in the valleys on the south side of the Pennines, much of the detailed geology is well exposed, particularly in the Maggia Valley. Valleys like this were gouged out by glaciers, but all the permanent ice has long since disappeared, despite the fact that there's snow on the ground here for over 6 months of the year.
Here in the center of the Alps, the rocks are much more deformed. These blocks are all sediments and of much the same age as those we looked at earlier. This isn't a sedimentary banding, that's all been obliterated. But rather, this fine compositional layering is a schistosity, produced by chemical segregation during metamorphism and deformation. This rock's a mica schist, and it's had a complex history. Here's a flat-lying fold lying in the plane of the schistosity. And they were both probably formed at the same time. But these tiny folds and crenulations deform the schistosity, and so must be younger. Such deformation and metamorphism is typical of that which has affected the sedimentary cover in this area. And it's much more extreme than anything else we've seen in the Alps so far. But even more important is that in this area, such deformation and metamorphism also affect the rocks in the underlying basement.
Further down the Maggia Valley, at the village of Lavatrezzo, powerful meltwater streams have eroded down into the basement and exposed large areas of rock. Here it's possible to examine in detail the complex, small-scale structures that typify the Pennines. The banded basement gneisses and granites have been deformed and folded in the same events which affected the overlying sedimentary cover rocks. And here and there, caught up in the deformed basement, are also a few lenses of sedimentary strata. There are many folds exposed in cross-section. And where the exposure is good enough, we can ensure that we're looking down the plunge of the fold axis. M-shaped minor folds are found around the nose of the fold. If we take a look at minor folds on the limbs of the main fold, we can see that on the left limb there are Z-shaped folds. And across on the right limb, there are the complementary S-shaped folds. This relationship between M, S and Z-shaped minor folds around a larger fold is just the same as those that we saw on a very much larger scale in the flat-lying Helvetic nappes. These structures are several thousand times larger than those in the Pennines. But in detail, the Pennine rocks are complex, and they deform very differently, depending on whether they're massive and homogeneous, or whether they're banded, and whether there's a difference in competence or strength between successive layers. In order to understand how folds in natural rocks may have formed, it's helpful to try and reproduce them under laboratory conditions. In the laboratories of the ETH Geology Department in Zurich, experiments are being carried out in an attempt to recreate the conditions under which some of these folds are produced. Hot waxes are cast to construct layered models which represent layered sedimentary strata and banded basement rocks. Each layer has a known strength or competence. In this particular model, the red layers are much stronger than the white matrix wax. When these layers have been fused together, the block is then placed between motorized pressure plates, which can be slowly pushed together. The machinery is driven by a computer, so that the rate of compression can be controlled accurately and recorded. Here, the experiment is speeded up 200 times. This speed is several billion times faster than rocks deform in the natural environment. As the pressure plates are pushed together, simple parallel folds are formed, and the thickness of the individual layers does not change very much during deformation. Drawing circles on the wax before it's squeezed makes it much easier to see the effects of deformation. To begin with, this layer thickens as it is compressed and shortened. Many of the circles are squashed and become elliptical before the folds begin to develop in the dark layer. When the folds do start to form, the material inside the nose of the fold is highly compressed. Here, the circles become flattened and stretched out. But around the outside, the material is less deformed. The circles are still more or less circular. In real life, there aren't nice, convenient circles drawn everywhere, but these do allow us to examine what goes on during folding. It reminds us that when we study deformed outcrops, we can only hope to assess the sum total of all the deformation they've experienced, and certainly not chart the many and varied ways they came to their present shape. Sometimes, for example, in banded rocks, the individual layers can have quite separate fold patterns. If the difference in competence or strength between the layers is changed, then the style of deformation changes. Here, the red and green layers are of the same thickness, but the green layer is much more competent than the red layer. As a result, the red layer is compressed into folds with much shorter wavelengths than the green layer. In other words, disharmonic folds have been produced. Disharmonic folds are when axial planes of one layer can't be traced through to the next layer. It's also possible to produce disharmonic folds in layers of similar competence when there's a big difference in the thickness of the individual layers. The thicker band is deformed into a few larger wavelength structures, while, under the same compression conditions, the thin layer has crumpled into a succession of tiny disharmonic folds. But this is nothing compared to the complexities of real geology. The relationship between thickness and fold wavelength can be seen very dramatically in some penine outcrops. Where the original layer or band thinned out into a wedge, it forms a series of increasingly shorter wavelength folds towards the thinner end. These laboratory examples have concentrated on one phase of folding. But as we've already seen, the alpine mountain building event was complicated, and in many areas the rocks experienced more than one phase of alpine compression.
In this outcrop, we can see a synformal fold with a vertical axial plane. When we follow in this structure the position of this pale-coloured gneiss band, we find that it curves around the synformal hinge to this position, then it returns and is folded by the same synform. This implies that there must have been an earlier fold whose axial plane is in this position and which has itself been refolded by the synformal structure. I can make this clearer with a piece of paper. The first structure had an orientation like this, and it was subsequently refolded to develop the later synform. When we measure the orientations of the fold axes and axial planes of these structures, we find that they are parallel to folds that are found in the Mesozoic strata. And this means that these two sets of folds here are both of alpine age.
All these structures are relatively small scale, and they are most spectacularly developed in rocks which are highly banded or layered. In these banded gneisses, the fold patterns are much more irregular and extremely difficult to work out.
But of course, much of the basement in the Pennines consists of massive igneous granites. Because compositional layering is generally absent from these granites, the rocks respond in a quite different way from the banded gneisses. Instead of folding, they form zones of high deformation known as shear zones. This granite has a well-developed foliation, and you can see as we trace the foliation through the shear zone, we can determine the sense of motion on this shear zone. It is in fact a left-handed shear zone. In this outcrop we also find shear zones which have a different orientation and a different sense of motion, shear zones which are right-handed. And these two sets of shear zones form what is known as a conjugate set, which enables the rock as a whole to shorten in this direction and to extend in this direction. Another interesting feature about this shear zone is that strong recrystallization and rock melting has taken place along it. And during deformation, this melt may be squeezed out and form cross-cutting dikes.
This whole area is in fact cut by numerous dikes. This large dike must have been intruded into the basement rocks fairly late on in the alpine orogeny, because it cuts right through the structures in the highly deformed basement gneisses. These dikes have been intruded in a number of different phases. Here there are two dikes. The thick, undeformed one is the youngest, and it cuts through the older, thinner one, which was folded after it had been intruded. In this outcrop, there are another two cross-cutting dikes, but both of them have been folded after intrusion. We can compare the amount of shortening by comparing the lengths of the dikes over the same distance of outcrop. The upper dike has obviously been compressed a great deal more than the lower one. In other words, it must have been intruded and folded before the lower one. After both of them had been intruded, there was a second phase of compression and folding. These are some of the more complicated deformation structures that we've seen in the Alps. In our journey across the Swiss Alps, one of the most striking aspects is how the style and complexity of deformation has changed from the outer Helvetic zone to the core of the Pennines. To contrast these two zones, it's worth taking a look back at their different types of structures. The great nappes of the Helvetics are large, broadly simple structures in which near-shore sediments were transported northwards. It's impossible to see the nappes in their entirety, and even the minor folds around the nappe take up whole cliff sections. This Helvetic folding had comparatively little effect on the underlying pre-alpine basement of the Mont Blanc range and the Aiguille Rouge. But in the Pennines, all that changes. The sedimentary cover rocks were deformed along with the underlying basement schists and gneisses. This basement, far from being passive, was embroiled in a succession of deformation and intrusion events, with the style of deformation changing from complex interfolding in the banded basement rocks to discrete shear zones in the coarse, massive granites. So, by examining the Pennine outcrops in detail, we've been able to see that here the alpine orogeny was typified at depth by repeated deformation and folding, melting, and finally dike intrusion. Some of these structures are present in the high Pennines, but for obvious reasons they're difficult to examine in detail.
The tectonic processes which form the Alps started about 150 million years ago, when the two continental plates bearing Italy and northern Europe started to move together. All but a few fragments of the intervening ocean crust were destroyed by subduction, and when eventually the continents collided, the crust was thickened and deformed as the European plate was dragged down beneath the Italian one. And that crustal thickening resulted in the metamorphism, which is now characteristic of the core of this mountain belt. Yet even that's not the end of the story, for the Alps are still evolving. All around, they're being eroded very rapidly, and the crust is rising at a rate of about 1 millimeter a year. Now that will presumably continue until this piece of crust once again resumes its normal thickness. And by that time, a staggering 10 or 15 kilometers of rock will have been removed from some of the areas we've visited. All that material will be redeposited elsewhere as sediments, leaving a linear strip of high-grade metamorphic rocks where the Alps used to be.